Have you ever wondered what the actual hidden speed limit on AI is right now? It's not just compute power, and it's not just data. It's a toll booth. Believe it or not, evaluating a single modern AI agent on a complex task can cost over $1,000. When you're trying to build the future, hitting a $1,000 toll booth every single time you want to test a new idea is a massive bottleneck. Think about that for a second. We're in an industry that's literally defined by lightning-fast iteration, right? Yet running a single evaluation can cost thousands of dollars and take days to complete. While the AI models themselves are developing at breakneck speed, the very tools we use to measure their progress are dragging us down with heavy financial and time burdens. We are facing a serious AI evaluation crisis. Welcome to This Explainer. Today, we're unpacking a truly groundbreaking research paper from Carnegie Mellon University and Salesforce AI. They've tackled this exact crisis head-on with a mathematically elegant framework called PACE. By the end of this explainer, you'll see exactly how they managed to cut these astronomical testing costs down to almost nothing without sacrificing accuracy. Okay, here's our roadmap for this explainer. We're going to cover 1. The AI evaluation crisis, 2. Introducing the PACE proxy, 3. How PACE actually selects tests, 4. Matching quality at 1% of the cost, and finally, decoding AI agent skills. Let's get into it. Part 1. The AI evaluation crisis. So to really grasp this bottleneck, we need to look at how we test AI right now. It's kind of like the movie Moneyball. On one hand, you've got your highly expensive superstar tests. These are your agentic benchmarks like SWE Bench and Gaia. They make models operate over long horizons, interact with complex environments like web browsers, and recover from errors. They are brilliant, but they take literal days to set up and run. On the flip side, you have your not-agentic benchmarks like MMLU or Human Eval. These are the cheap, undervalued atomic tests. They're single-turn, incredibly fast, and cost just fractions of a penny to run. Which brings us to part 2, introducing the PACE proxy. This massive price gap begs a pretty fascinating question. What if we could predict how that expensive superstar is going to perform just by looking at its cheap stats? Well, enter PACE. That stands for Proxy for Agentic Capability Evaluation. It's basically our hero for this explainer. PACE proves you don't actually need to run a $1,000 agentic test if you can find a tiny, highly curated group of those cheap, non-agentic tests that predicts the exact same outcome. It's all about building a proxy benchmark that gives you the exact same signal using just atomic capabilities, like basic instruction following. All right, moving on to part 3, how PACE selects tests. So how exactly does PACE draft this perfect, low-cost team of proxy tests from a sea of thousands of available benchmarks? It basically creates a brilliant mathematical map. PACE takes a calibration set of models, ones where we already know their scores on both the cheap tests and the expensive tests. Then it fits a least squares regression. You can think of it like drawing a perfect line of best fit that connects a model's scores on a few cheap source tests directly to its expected mean score on that pricey target agentic test. But wait, how does it pick that specific subset of cheap tests in the first place? PACE strategically drafts a budget of, say, 100 tests, using 2 complementary moves. First up is global selection. This looks at overall geometric importance, essentially using a math tool called SVD leverage to find the most diverse, information-rich tests and multiplies that by target relevance. Then there's local selection. This ignores the broad geometry entirely and just hunts for tests with the highest direct correlation to the target. By combining these two, PACE makes sure it doesn't just pick redundant tests, it builds a perfectly balanced, predictive ensemble. There is a slight catch, though. Because those expensive agentic targets cost so much, they usually only have a few hundred instances. So the target scores we're trying to predict are inherently noisy. To fix this, PACE does something super clever. Bootstrap resampling over the target instances. By resampling the data over and over, it averages out that noise. This stabilizes the math and stops the framework from just memorizing some quirky overfitted pattern. Part 4. Matching quality at 1% cost. Okay, but does this actually work in the real world? The researchers tested this across 14 different cutting-edge language models and 4 major agentic benchmarks. And this chart here is the huge reveal. We're looking at the cost versus quality trade-off. The blue line is our PACE proxy, and the red line is what happens if you just randomly subsample the expensive test to save a buck. Just look at how the blue PACE line completely crushes the red baseline. PACE hits peak prediction accuracy way over to the left of the chart, meaning high quality for practically zero budget. The predictive power here is just undeniable. And they didn't cheat. They used a strict leave one out cross-validation protocol. That means they asked Pace to predict the performance of a completely unseen, held-out model. The results? A mean absolute error of under 4%. A Spearman rank correlation of over 0.80, which means it accurately ordered the models from best to worst. And if you just ask it to compare two models head-to-head, it picks the true winner about 85% of the time. That is wild. Which brings us to the ultimate payoff, 100 times cheaper. Developers can now get highly reliable estimates of how an AI agent is going to perform in the wild while slashing their evaluation budget down to just 1% of the original cost. 1%. You can screen models, monitor training checkpoints, and run dense feedback loops in minutes instead of days. Finally, part 5, decoding AI agent skills. Now, cutting costs is amazing, but it's actually only half the story. The researchers realized Pace gives us this fascinating, almost accidental secondary benefit. It literally lets us peek under the hood of AI agents to see how they think. Since Pace automatically selects cheap proxy tests to predict the expensive ones, if we reverse engineer exactly what it picked, we get this incredible, interpretable heat map. It shows the unique DNA of underlying skills required for complex tasks. Since we know what abilities the cheap tests measure, like math, coding, or visual understanding, we can see exactly what's driving success on the big benchmarks. For example, let's look at SWE-Bench Verified. This is a repository-level software engineering test, a coding benchmark, right? But the chart reveals that success here actually hinges heavily on multimodal understanding and information retrieval. Even though it's a text-only patch generation task, the ability to sharply discriminate visual info and pull relevant data from a massive pile is what actually separates the good models from the great ones. Who would have guessed? And we see this unique mapping everywhere. Contrast that coding benchmark with Gaia. Gaia heavily relies on strict instruction following and self-verification because it's answering complex web-based questions. Or look at SWT Bench, where the model writes tests for bugs. It uniquely demands heavy planning skills. Pace proves we can automatically profile task requirements without needing expensive, time-consuming human annotation. The math simply tells us what matters. So, I'll leave you with this provocative thought to ponder. For years, we've worried that the sheer expense and complexity of testing advanced AI would slow down progress, keeping the best development locked behind the doors of only the most well-resourced labs. But if evaluating complex AI agents is suddenly 100 times cheaper and faster, how will this accelerate the arrival of the next generation of AI? When you remove the biggest financial bottleneck in testing, the pace of future innovation really does become limitless. Thanks for joining me for this explainer, and I'll catch you next time.